So the final thing we have to cover here is box D, which I've titled here Applications Using Trigonometry. What these basically are optimization questions, just like we saw back in Unit 15. Only this time we're going to be using, obviously, trigonometric derivatives to solve these problems. So we're going to follow essentially the same steps that we followed back in Unit 15. The only difference is, the trig derivatives here. So here's our first example here. What is the maximum area of a triangle that has a hypotenuse of length 1 over root 2? We'll just draw in this root symbol here. So just like in Unit 15, the first thing we should probably do is sketch ourselves a diagram here. So we've got a triangle. We know it's a right angle triangle because it has a hypotenuse. We know the length of the hypotenuse is 10 root 2. And that's about all we know right now. So what are we trying to optimize in this question? We're trying to optimize the area. So what we need is an expression for the area here. And so we can start from our basic geometric formula, 1/2 base times height. This is our base, and this is our height. And what we need is our base and our height expressed in terms of one variable, because we need a function of a single variable in order to take the derivative, set it equal to 0, and so on and so on. So what we want to do is we want to use this angle in here. We'll just call it theta. And we want to express both B and H in terms of that angle there. So if we look at this triangle, we can say that, well, sine theta is going to be opposite over hypotenuse, so that's H over 10 root 2. So we can rearrange that to get our expression for H. The height of the triangle is going to be 10 root 2 times sine theta. To get our expression for B, we can look at, again, this triangle and say, okay, if we do the cosine of theta, we have adjacent over hypotenuse, so that's going to be B over 10 root 2. So B is just going to be 10 root 2 times cosine of theta. Let's fix that a little bit. Cosine of theta. And we can sub those two expressions into our area formula. So our area is going to be 1/2 times our base is 10 root 2 cosine theta times 10 root 2 sine theta. And we can clean this up a bit. Root 2 times root 2 gives us 2. And that 2 is just going to cancel with this 1/2. Okay, so those guys are going to go away. And then we've got 10 times 10, which gives us 100 cos theta sine theta. So that's our expression in terms of one variable. Yeah. Before we do that, before we do the derivative, set it equal to 0, let's think about the domain of theta here. Are there limits on how big and how small theta can be? And it's helpful just to look back at the diagram here. I'll just write this in here. We can put an upper limit and a lower limit on this thing. Okay? If we imagine theta getting bigger and bigger and bigger, we can't make it any bigger than 90 degrees. Because if we made it 90 degrees, if it was equal to 90 degrees, we wouldn't have a triangle anymore. Because we'd have a right angle here and a right angle here. So clearly, it's got to be less than 90 degrees. And if we make it smaller and smaller and smaller, well, we can keep making it smaller until it gets to 0, at which point we've got just a straight line. Okay, so we can't make this any smaller. It can't be equal to 0, otherwise we don't have a triangle. Now this is important because if we're looking for solutions between 0 and 90 degrees, if we think of this in terms of the angle and standard position, we're in quadrant 1. Okay, which means we don't have to worry so much about the signs of our trig functions because quadrant 1, all of our trig functions are positive. Okay, so this is So this seems like sort of an extra step, but it's important in terms of how we're going to get our solution. So now we want to move on and we want to do our optimization. We want to take our derivative and set it equal to 0. Okay. Our function here is in terms of cosine and sine, which is good. Cosine and sine are pretty easy to work with. So our derivative is going to be 100 times the derivative of cos x times sine x. We've got to use product rule here. So if we do product rule, we need derivative of cosine, which is negative sine theta times sine theta, okay? Derivative of u times v, plus our u function, which is cos theta, times the derivative of sine, which is cos theta. And those are square brackets at the end. So 100 times cosine gives us cos squared theta, and sine times sine gives us minus sine squared theta. And we want to set this equal to 0. Now, how can we solve this? What can we do first? Nick. Let's deal with the 100 first. No, we don't even have to do that. We don't want to do that. First, get rid of the 100. Let's divide both sides by 100. 0 divided by 100 is still 0. So now we just have cos squared theta minus sine squared theta. Okay. No. If I did cos 2x. No, we don't need to use an identity. Okay. Let's bring the sine squared over to the other side. It was negative sine squared theta, so that becomes positive sine squared theta equals cos squared theta. Okay. At this point, we can take the square root of both sides and get sine theta equals cos theta. Now, we can do that because we're working in quadrant 1. And we know that both sine theta and cos theta are positive. Had we been in quadrant 2, one of them would have been, what is it? Sine is positive, cosine is negative. When we squared them, they would have been the same. But we have to consider positive and negative here. But because we're in quadrant 1, we know that both sine and cosine have to be positive. So I'll just say because we are in quadrant 1.
But if they're in quadrant 2, can you put like a negative in front of it?
Yeah, you'd have to work out what's positive and what's negative. Yeah. You.
Yeah, it just makes sine theta equals negative cos theta.
Yes. Yes, I think so. Okay. So yeah, you'd have to work out what the signs are going to be, basically. But from here, what can we do? Well, let's divide both sides by cosine theta. Sine theta over cos theta is 1. Sine theta over cos theta is tan theta. So theta is going to be inverse tan of 1. This we can punch into our calculator and get a solution. And as Brody has said, the solution is going to be 45 degrees. Okay?
I saw the special triangle. I said the only way that sine can equal cosine is if
Yep.
they're broken.
Yeah, so you could have recognized that from the special triangle because you've got that 1, 1, root 2 triangle. 45, 1, 1, root 2, and we'll do that. Okay?
So we could essentially solve advanced functions questions using this.
Possibly. Depends on the question. Yeah. So from here, we've got our solution. We should check to make sure that this is actually a maximum. So we're going to use our second derivative test here. So I might have to, this is a lot of stuff. Let's move on to another page here. So our first derivative was 100 cos squared theta minus sine squared theta. Again, square brackets. Let's take our second derivative, which is going to be 100 times, if we do the derivative of cos squared theta, we got to bring down the 2. So 2 cos theta times the derivative of cos theta, which is minus sine theta. So I should actually write that by, put the negative sign out front, so it doesn't look like I'm subtracting. Sine theta. This is going to be minus derivative of sine squared theta, which is going to be 2 sine theta times the derivative of sine theta, which is cos theta. Can simplify this to, because those are the same thing. So negative 2 cos theta sine theta minus the same self is going to be negative 4 cos theta sine theta. And this is where the fact that we're dealing with a 45-degree angle comes in handy. Because if we evaluate this at 45 degrees, we know from that special triangle that cosine theta, sine theta are going to be the same. They're both going to be 1 over root 2. So 1 over root 2 times 1 over root 2 is just 1/2, times 4 is negative 2, times 100 is negative 200, which is less than 0. So we have a local max. Which is what we wanted. We wanted to get the maximum area. Richard? Yeah, you've done something wrong. Yeah. In this course, if I'm asking you for a local, a maximum value, it's going to be a maximum value somewhere on that domain. Okay. So we got our local max. So theta equals 45 degrees is a good solution. We go back to the original question and we say, what was this question asking us for? It was the maximum area. So we have to go back and we have to find the area. So our expression for the area was 100 sine theta cos theta. Let's evaluate this at 45 degrees, which is just going to be 100 times 1 over root 2 times 1 over root 2, which is going to be 50. And that's our final answer. Therefore, the max area is 50. So in this question, we're told that we have a ladder that is to be moved horizontally around the corner from a 3-meter wide hallway to a 2-meter wide hallway. We want to determine the length of the longest ladder that can make this turn, and we're ignoring the thickness of the ladder here. So the key to this question is the diagram. So I've got my diagram here. I've got kind of an L-shaped hallway. We start at 3 meters wide, and after we make the turn, it's now 2 meters wide. And this blue line that I've put in here represents my ladder. And the key is how you put the ladder in there. So I have drawn the ladder so that it touches the walls at 3 points. It touches one wall up here at the top, it touches the other wall down here on the 2-meter side, and it just touches this corner right here in the middle. Okay? And I could have drawn it slightly different. Like I could move this side here. Let's move this end over here like this. I would have to move this one down like this, though. Okay, so I always want it to touch in those three places. All right. So first off, what are we trying to optimize here? What are we trying to make as big as possible or small as possible? Okay. The length of the ladder. So we want to optimize length of ladder. Okay, and we'll just call that L. And the trick to this question is to take L, take the length of our ladder here, which is the length of this blue line, and break it up into two pieces at this point where it meets the corner. We'll call this one up here L1, and this one down here L2, so that the total length is L1 plus L2. I can break this into two triangles. One right angle triangle right there, and a second right angle triangle down there. And L1 and L2 represent the hypotenuses of my two triangles. So I want to express all of this stuff, or I want to express the lengths L1 and L2 in terms of an angle. And I'm going to choose this angle in here because I know this angle is going to be the same in my two triangles. We'll call that theta. So looking at the top triangle, sine theta, which is opposite over hypotenuse, is going to be 3 over L1. So L1 is going to be 3 over sine theta. Looking at the bottom triangle, I've got to work with the adjacent side. So cos theta is adjacent, which is 2 over hypotenuse, which is L2. So L2 is going to be 2 over cos theta. So I can sub those two expressions in to my formula for the length. Length is going to be 3 over sine theta, plus 2 over cos theta. And the limits that are going to be placed on theta are going to be the same ones that we had in the previous question. Okay, it's got to go between 0 and 90 degrees. Okay. I mean, in principle, I guess it could equal 90 degrees. Yeah, I guess it can actually, in this case, be equal to those two like that. Okay. Okay, so now we've got the expression for what we're trying to optimize, length of the ladder, expressed as a function of a single variable. We can take our derivative and set it equal to 0. Now, the textbook does a couple of examples like this, and what they do is when they have 1 over sine theta and 1 over cosine theta, they replace them with 1 over secant and 1 over secant and cosecant. I prefer to leave them as sine and cos because it's easier for me to remember the derivatives of sine and cos than to remember the derivatives of secant and cosecant. So I just like leaving it in terms of sine and cos. And I do my derivatives from there. The choice is up to you, though. So if I'm going to leave them as sine and cos, I'm going to rewrite this as 3 sine theta to the -1 plus 2 cos theta all to the -1. And then I'm going to take my derivative. The -1 comes down. Sine theta to the -2 times cos theta, applying the chain rule. -1 comes down, giving me -2 cos theta to the -2 times the derivative of cos theta, which is negative sine theta. I want to set my derivative equal to 0. And if I put my negative exponents back into the denominator, I'm going to have -3 cos theta over sine squared theta plus 2 sine theta over cos squared theta. to solve this, I can solve it in a very similar way to the way I solved the previous one. I've got one expression that's positive, one that's negative, so I'm going to bring the negative one over to the other side, which is going to give me 3 cos theta over sine squared theta equals 2 sine theta over cos squared theta. And now I'm going to cross multiply. Because when I do that, I get all of my cos terms together and all of my sine terms together. 3 cos cubed theta equals 2 sine cubed theta. And then I can divide through by cos cubed theta to get sine cubed theta over cos cubed theta. Divide through by 2 to get 3 over 2. This is good because sine cubed theta over cos cubed theta is tan cubed theta. And so I can solve this by taking the cube root of both sides. Cube root of 3 over 2, tan theta. So theta is going to be the inverse tangent of the cube root of 3 over 2, which I can punch into my calculator. And because I know I'm working between 0, the theta has between 0 and 90 degrees, whatever my calculator spits out is going to be my value for theta. Okay. All right, so who's got a calculator that can punch this in? I've got the solution here, but I did it in radians. And I wrote my domain up there in degrees. So I suppose I could convert it in my head here, but I can't. All right, 48.86 degrees. Okay. Okay. So that is going to be the angle, okay, in that diagram that is going to be optimize our length here. So now we need to take this solution, plug it back into our original equation for the length of the ladder to figure out how long that is. So the length of the ladder was 3 over sine theta plus 2 over cos theta. I believe. If we skim back up to the top here. All right. So we evaluate this. Sine 48.86 cos 48.46. We punch all that in, and 7.024 meters is our answer. Okay. Where I've skipped the step of checking that this actually gave us a maximum using the second derivative. Okay. But the important thing is here is how you get that original expression that you have to take the derivative of, and how you solve it by turning our two sines, cosines, into this tan function that you can then do the inverse tan on. Okay? And that's the end.